Okay, folks, I think we will get going. There's a few folks online. I did send out a little message out to some interested parties, so some folks will probably be filtering it as we continue on in the session. This is the last session now, or the last group of sessions before the meeting breaks, and so thank you for sticking it out and coming here to participate. And this session is new paradigms for alternative data packaging of geolocation information for Earth observation data. Co-session leads are Ed Armstrong, myself, and Alex Jelinek from the HPF group. I'm from the NASA JPL PODAC, one of the 12 NASA data centers. And so the motivation behind this, I don't know if this is quite a true statement. Maybe this is some of my bias in here, but there is some substantial footprint for geolocation information inside the EOS DIS archives that represents, some difficulty sometimes for download and service requests of data by users. So, I mean, there have been requests to look at, the geolocation footprint. All this applies more to level 1, level 2 data than gridded data products. And within the NASA Earth System Data System Working Groups, there's the data set interoperability. So that's a collection of, NASA interested principals, scientists, and engineers that are working on data interoperability issues. And we have formed this geolocation representation subgroup. It's actually a new name for this year as part of the dataset interoperability to look into this. And we've had 2 telecons so far, as well as this session that will give us an opportunity for a deeper dive. So just kind of looking back on the past horizon of our alternative ways of reducing the geolocation footprint within data granules. There's examples in the past and early in the EOS DIS MODIS missions where they package geolocation in a separate granule that was shared, one separate granule that was shared then commonly with other granules of different parameters. And the idea there was that, the granule that has the same timestamp was the one you want to use for the geolocation for the particular parameter of interest. As well as also the ocean biology processing group, they actually did some geolocation decimation and then had a little algorithm to rebuild those missing geolocation pixels on the fly. So something they had implemented in a software reader. And there might have been a few others, but they all had kind of their flaws. For one thing, they were often awkward for scientists to work with, and they were really impossible for software and service developers at that time to really work with and develop towards building an API framework for. So, but there are some new best practices and, technology and things move forward, and that's what we're going to be looking at here in this session. Things in the CF conventions and the HDF5 data model. I mean, I learned the other day in the CF workshop about this external variable reference, and that's being proposed in CF 1.8. So if we have some time, we might want to circle back and look at that. There are some people in this group that are going to be looking at that in this geolocation representation group. As well as better ways, more elegant ways of handling projections and remapping. There are new ways of indexing geolocation data, totally new. That, for instance, STARE, and we're going to hear about that this morning. As well as we need to think about what does it actually mean geolocation in the cloud data storage paradigm, right? For analysis ready data. We're no longer going to have individual granules in that particular paradigm. So we need to think about, how does perhaps can geolocation be shared around different parameters in that kind of framework. I guess, but for each in the back of our mind, I mean, we're not all software developers. I'm certainly not a hardcore software developer. We need to think about, for each of these approaches, what is the, what is the impact on the services and software development side. And hopefully this can guide further discussions within our working group. So with that, we're going to have 4 presentations today. Quo is going to start off with STARE, and then Alex will HDF5 and external references. Then we'll hear from Robert Wolf, and then I'll do cleanup last. So Quo, come on up, and I'll get your presentation loaded up here. All right, there you go.
I retitled this presentation to Integrative Analysis Ready Data with STARE, and the Integrative Analysis Ready part is the new content, but most of us here, especially if you're in the external geolocation group or subgroup, splinter group, You have seen most of the slides. So outline, first I introduce or describe the integrative analysis problem, and then propose STAIR as a solution. And I go through STAIR a little bit. I'm going to go through them very fast because I presented all those things before. And then conclusion, actually I've gotten rid of the relevant references. All right, no echo. Okay, so the integrative analysis problem, this is basically caused by the dissociation between the array indices and the geospatial temporal references. And that dissociation severely impacts, in a negative way, our integrative analysis. I will explain that in a little bit more. So you are very familiar, especially I see mostly NASA people, and you're very familiar with this EOS data model of a grid, swath, and a point data, except for the grid. The grid, when the grid here is actually a regular latitude, longitude grid. So the indices of the array then has a linear relation with the geolocation. But that's not the case with the swath data. Actually, that even there, the relation is not fixed because it could change from data set to data set if the resolution change. All right, then it's definitely not the case with the swath and a point. Swath, the indices are correlated with geolocation, but there is no fixed relation. All right, so the gist of the problem is that earth science data are predominantly geospatial temporal, and they are predominantly expressed in array data structure. And then the integrative part, so most of the earth science integrative analysis requires spatial temporal collocation, meaning that analyzing diverse data sets for the same space and the same time, or rough space or rough time. All right, but then, as you know, that we have just getting more and more volumes of data, and then in order to handle that, to scale volume, and the only way is parallel processing. I cannot think of another way to scale volume, right? But then when you scale volume using parallel processing, you need to have consider data partitioning and the distribution. So now, without a fixed relation between your references, between the array references and the geospatial, your physical dimension references, it will be very hard to collocate, among diverse data sets, collocate the data spatial temporally. Okay, so this is after the first day. I got an inspiration from the big gridded data group. So basically, there are physical dimensions, and then there are corresponding, or roughly corresponding array dimensions. But they, but presently, the way we package data, there is no constant correspondence between these two kinds of dimensions. So, but our analysis are ultimately concerned with the physical dimension. I mean, we don't care about the array dimension when we do the analysis, but then we are forced to go through this array indices, array references, in order to get to the physical dimension references. But this relation is not fixed. This is what's causing the variety problem. As far as I can see, the key variety problem in processing, especially integratively processing earth science data. Then STAIR is an attempt to establish such a fixed, constant correlation, relation between the array index references and the geospatial physical references. Okay, so this is a stair design. Stair has two parts, a spatial element and a temporal element. And it's try to establish a fixed constant connection between the indices and the geospatial temporal references. And the one thing that Stair is unique about it is it has a reference to the resolution of the data elements both in space and time, because the resolution is also a spatial temporal property of the data elements. So with this, we believe that the Stair can facilitate effective scaling in both volume and the variety to lead to maximized throughput, therefore scaling velocity as well. Okay, so most of you have seen this. Basically, this is how we construct the Stair spatial part using the hierarchical triangular mesh. And this naturally leads to 8 quadtrees. Okay, this is the view of the quadtree. So we start with the octahedron, which has 8 sides, 8 triangular facets. You can number them using 3 bits. And then each qualification uses 2 more bits. So you keep going on, but we store left justified as Mike described it, because we start from the more significant bits and down. Okay, the 3 bits will be, the first 3 bits will be in the more significant part. Then we use the next 2 bits at a time, pairs of bits at a time for each qualification. So what we ended up is that we reduced the 2D indexing to 1D, and there are some really nice properties, hierarchical. So and the indices are consecutive. So if their index is close, then for most of the times, then the location is also close, and so on. And with 57, we use 57 bits to go down the qualification 27 times, and then that reaches a resolution better than 10 centimeter in diameter. And as I mentioned there, at the 23rd qualification, you have already reached the 1 meter. Okay. And we used 57 bits plus a sign bit that we are not using because it's always positive, and then we have 6 bits left that used to indicate the approximate data element resolution. So what happens is that if in this qualification scheme, this hierarchical quadtree scheme, if you pick a branch to cut, then within all the data within the branch, it direct to all the way down. So everything together, right? So you can use that as a chunking mechanism and the partition the data. So all the sub branches can go to down to the leaves, can go to a cluster. A cluster node. I'm sorry. So this will provide a very convenient partition distribution scheme. And if we use this across all the data sets, then we can guarantee that for the same space and the same time, they will collocate on the same node. This is an example of this qualification and the scheme, and most of you have seen this. And the last 6 bits are used to denote the branch point, the branch level qualification level that correspond to best to the data elements resolution. All right, so this is a resolution chart, and depending on the qualification depth. And this is a graph that Mike made. So there are 16 gray shades, and each gray shades occupy level 4, I believe. Level 4, right? Level 4 qualification area. So all the points falling into the same shade can go onto the same node if you have 16 nodes. And then you can, kind of distribute it in a somewhat random way like we've shown here. And the overlaid on top is a swath, is a modus, Terra modus swath. And those points on the swath, which shade they fall on, then they will go to the corresponding node. So this is a way to partition and distribute the data and guarantee spatial temporal collocation. All right, so we talked about the application. This is basically just reiterate what I just said before. If I have a node, obviously a naive way is to put each branch on each node, but that branch will cover a large area. So if you are working on a small area within that area, what happens is that most of the other nodes will be idle, and you're just one node working. That's called a load imbalance, right? And so we want to use a smaller chunk size partitions. So for the integrative analysis packaging, what we are thinking of is leveraging the virtual data set capability of HDF, and we package the granule in these stair hierarchy. And in other words, right now we package them, in the swath, along the swath and so on. But, we just carve them into triangles, stair triangles, and then package the triangles. And then what happens is that you could use the virtual data set capability to basically emulate different qualification level. So in the cloud, if you imagine this, if you have big resources, you want to process, large volumes, great coverage in the entire globe, and you can afford to use very fat node, many of them, then you could start using the shallower level of qualification, which gives you a bigger chunk size, right? But you can go down and get all of them through this virtual data set. Now, if you are a small and you cannot afford a whole lot of cloud resources, you can start only maybe 4 nodes or 8 nodes, then you can, and the thin nodes, and then so you cannot afford using the big chunks for your partitioning or distribution. Then you go down to the deeper level. Then when the chunk size and also the data volume will be per chunk will be smaller. So this gives you a flexibility in cloud if we could package the same way. But the problem is that then how do we make it backward compatible? So people right now using the current packaging do not have to change their code. That is going to be our access proposal. Next one, yes. Our next one. Any case, well, this is why it's not advancing. I messed something up. Maybe it's because it's not selecting the. All right. So this is a conclusion. I basically have mentioned this a few times, but I think you can read them. And once again, I want to thank NASA Access Project for the current funding for STAIR, And I want to thank also the NASA AIST program for getting us started. The stair idea actually came up a few years ago with an AIST project. All right, questions?
Hello, Peter Leonard online. I have a couple of questions.
Go ahead, Peter.
Okay, first question is, I've heard Quo speak a few times, and I think this stair thing is very intriguing and has great potential. And so I'm going into more detail. Well, this is an easy question. First, the first incarnation of stair is to create a companion file, which has all this indexing in it. And so you'd have your original science data file, including the geolocation, and from that you'd create the stair companion file, which allows easy correlation with other data sets. So my question is, how long does it take to generate one of these stair companion files? Can it be done on the fly?
I think Mike Riley will be the better person to answer those questions, and also James, OpenDAB also have been trying to do this. So, but you know, James is not.
Let him swallow his food.
So the purpose of the question is that if it doesn't take too long to generate one of these things, then maybe you don't really even need a companion file. You would just generate it as needed and then dispose of it.
Mike, go ahead.
Yeah, this is Mike Riley. The hope is that it'll all be cheap enough that you could actually do that. However, I've not measured that amount, just how long it's going to take. So, but from my initial experiments, it doesn't take that long. I don't know if it's fast enough to be able to do interactively in that way. But once you do run it, the companion file doesn't take up a lot of space. So I guess the fundamental thing is that's something that we're looking for. We're interested in finding out precisely how long that's going to take. And I'm hoping that you'll be able to do it online, and with luck, you'll be able to even do it interactively.
At the very least, that in our STAIR project, we have a plan, intention to look into that using within OpenDAB to translate that on the fly, but we don't know, we haven't gotten to that part yet, so we don't know how feasible that is.
But that would leave a lot of the benefits of STAIR sort of on the table, because the other things you would want to do with this is create more efficient database lookups,
yeah,
right, matchups, things like that.
Right.
And I think for those cases, you really do need to pre-compute them instead of computing them on the fly for the whole repository.
That's right. That's right.
Okay, I have a second question. Second question. So let's say STAIR companion files are necessary to move forward. This is a really easy question, but will they easily compress?
Yes, actually, we have looked into that. We believe that it has better compressibility than latitude longitudes. Because, you know, STAIR is a hierarchical, so a lot of those bits for the nearby data elements are going to be the same. So that's why we hypothesize that it's going to be more compressible than latitude longitudes.
Okay, we have one more final question from Jim Biard.
Hi there. Yes, so the thing I was wondering was, I see this as being really incredibly useful for doing like co-location, all those things you've been talking about.
Yes.
But a lot of times when you're done, you want to go back to a grid in practical terms.
Yes.
So I'm just wondering what's the general thought about how you're doing that? Are you providing support for that? Reverse, to round trip this basically.
Right. Yes. Actually, we had a project doing that before STAIR. It's called the Noggin, is for regrading, because once you can collocate things, you can have a coarse footprint, including many fine footprints. But that comparison is one to many. That doesn't make too much sense, right? So you have to homogenize that in some way in order to have meaningful comparison. That's what we did. Noggin is a NASA open grading project, and that project basically had all the mechanisms to do the geogridding, including kriging.
Okay, thank you. Well, we have to move on to the next
Okay.
talk. So if we have
Mike,
some
you have
time
to ask me.
at the end of the session for follow-up questions, we'll move on then. But we have to move on to the next talk, which will be from Alex. And I do apologize for the folks online that it appears that when we do the presentation, it's just in the presenter's mode for you online, but I don't know how to fix that if somebody wants to do that really quick. All right, so the important thing, we got his presentation up. If you can help us.
Go to, where is that? That's it, there. No, you would go somewhere here. Oh, is this
On the PowerPoint
PDF?
or?
Is this PDF or PowerPoint?
No, it's a PowerPoint. It's in the view.
View, right.
We're putting in present view, right?
Presenter view. No, you don't want presenter view. Shucks.
Yeah, we're using the presenter view is what we're projecting onto the screen. Yeah, that little button there. But when we do that,
Yeah, there we go.
Swap display?
You go there. Yeah.
Oh, use
Oh,
slideshow.
okay.
All right.
thank you, Rama.
Wow.
Now we learned something.
Extra applause
Okay.
to Rama. Yes, for saving this session from the media disaster.
Oh,
Yeah, that's cool. So I'm going to talk about some of the capabilities provided by the HDF5 library for external data access. And Quo mentioned the virtual data set. I'm not going to talk about it because that feature is more like what I would call data aggregation. I was more thinking to talk really about capabilities to connect two or more files together in some way, which is more of what currently I think is a more likely a use case, at least for now. And also, so that's basically just a little warning there. And I also have two of my colleagues for HDF group, so they can correct me if I say something that's not exactly correct as far as the HDF proper capabilities go. Which button? Oh, this one, yes. So the key element of the HDF5 that allows this linking is this thing called the HDF5 link, and it's the member of the data of the HDF5 data model, amongst other things. But the link is the key enabler here. And so HDF5 links are named associations between an HDF5 group and as a source and some target, which is another HDF5 object in the file. And the library essentially allows or implements two types of those links. One is called hard link. That one has to have the target in that file, in the same file. The soft link, on the other hand, can dangle. In other words, can go without the target. So imagine, imagine a bridge to nowhere, where maybe that bridge would finally be somewhere, but it's not right now. So that's basically the kind of the soft link. And that really, that feature of the soft link essentially makes it possible to do the external linking as one of the ways that I'll show here. And so very briefly, to the right is essentially an abstract representation of content of one HDF5 file. That's essentially a graph. And all these arrows that you see are essentially those HDF5 links. And those little letters next to them are their names. And HDF5 data model does allow kind of interesting capabilities. In other words, the link that points to the same object, or multiple, that one HDF object is actually the target of multiple links. Why are links important? Essentially, they provide the things that we called are known as HDF5 path name, or in the NetCDF world are known as the variable name and these kind of things. Essentially specifying that they are slash something, slash something, slash something. They actually, those are the HDF5 links and their names. And this would be essentially be a view of one file. The what is this? Yeah, bluish kind of rectangles there, the data sets, the folder-like shapes, they represent HDF5 groups. And I also included one octagon that represents a data type, but that's a little bit more advanced. We don't have to deal with that right now. So this is where we typically now have situation. We have two files with some kind of connection between them. And so far people have to open one, open the other one, read the data, that kind of thing. And the content here is not so much important, just sort of remember briefly, because we'll have to show some other capabilities here. But anyway, these are the two files. So imagine one of those files, for example, having, for example, geolocation data or something like that. The first way how these two files could be connected currently in the library is to mount them together. And what that means is that sort of similar to file systems, you could, for example, choose file 1, and you could in this case, mount file 2 into file 1 at a certain point in the hierarchy. And the way, the API function to do that is HPF Mount, and there is the link to the documentation for all the details. And the important things, however, are that this is a temporary connection. In other words, it only works while the application is running. So there is nothing in either of these two files that say that we are somehow linked, or that there is at least some kind of a connection that would expect to be linked to each other. The quirk of it is that you happen to mount file 2 to a group that already has the data sets or attributes attached to it. You're not going to have access to them anymore. So the best practice is to actually have an empty HDF5 group in this file 1 and sort of mount to that point the other file. And at that point, as I said, the other file content looks like just extension of the hierarchy going from slash file 2, for example. I just gave a name file 2, but you can give whatever other name you want. So this is mounting two files. It's a temporary thing. It has to be done on every run. The other one is externally linked to files. Now with this capability, if you see here, we mounted files. Essentially, we used file 2 and mounted its root group to some place in file 1. In this case, externally linking, we actually have ability to point inside the content of file 2, not from the root group, but wherever we want inside the file 2, and actually connect this linkage between file 1 and file 2. In this case, this external ext dset is the soft link in file 1, and we can create it and keep it in this file as a part of the file content. And so it's permanent in a sense that the location of the file 2 and where it links inside of it are stored as the definition of external dset link. And here is the link to the documentation, and there is a whole list of options how actually the HDF5 library goes about to find the file that was named as having the target of this soft link. There's a whole several paragraphs, all the gory technical details how that happens. But the bottom line, both of these cases are essentially expecting a file system, and these two files exist on some kind of a file system where application has access to. And obviously, we are now living in this world where things are moving to the cloud and file systems are, not anymore present. So, what could future bring? And this is essentially what I would close with. Again, obviously, we are now moving to HTTP-based data access, and by data access, I'm not thinking a web service API that provides data access. I'm literally now thinking about HTTP access that goes for bytes in some object, in an object-based storage. And so the library right now does have two ways that can reach out into the object storage. One is the S3 virtual file driver, which is a more basic, at the basic level of the library. And the other one is the REST API virtual object layer. That one requires right now highly scalable data server as a middleware between the HDF5 library and the object storage. The S3 virtual file driver does not require that. It goes straight to the, in this case, S3 compatible object store. So in the next major version of the library, if I'm not mistaken, so some of my colleagues from HDF can correct me wrong, I think it's due in September or roughly that time this year. There will be extension to this object and region references data types. I didn't mention them here because they are not currently available, but object data type is essentially a pointer to another object in a file. This is just a natural extension. Then instead of pointing to an object in a file, it's now going to be capable, like the external link or the soft link, to point into the object in some other file. And I mean, good thing about this approach is because the HDF5 objects can be stored in datasets or attributes, so they are storable information. Region references are just subsets of a dataset somewhere, so they are also going to be extended to point to some subset of some HDF5 dataset in another file. So that's going to be in version 1.12 as the natural extension of current capabilities. What would really be interesting, I think, regarding all this move to the cloud is if this external linking capability in HDF5 library would be able to support HTTP-based data access. So that instead of a file path, I'm providing a URL. And at that point, the HDF5 library just goes and hits that URL. And what would that capability open is that literally even the people who do not go to object-based storage, they could put their data behind a web server, a traditional web server. And as long as that web server would support range gets, the library would be able to bring the data into this case. It wouldn't be, the super scalable kind of solution, but it would provide a way to connect a file on someone's computer somewhere locally with some data that is somewhere else. And that's basically, yeah. And I didn't mention, obviously, the whole idea of sharding HDF5 files and the capabilities that now we have, like ZAR or like other approaches where you have a textual representation and then binary connections to that file that open up essentially linking that can happen all different ways. But that's, again, sort of a different, I thought this was a different topic in its own right. So this is more right now what can happen and what would be maybe a little more extensive way to do things. And that I think is the last one. Yes. So thanks.
Well, thank you, Alec. Any questions for Alec? Robert?
Alec, one of the, I guess my main question is about NetCDF. I mean, since HDF5 is underlying NetCDF,
yes.
but NetCDF doesn't have the same sort of soft link, hard link kind of convention. So how would you make NetCDF like understand this and then support these types of things?
Yeah, so I forgot to mention when I was talking that two things that I didn't cover here. First one is that there are no conventions right now that sort of cover any of these issues well. So sort of standards or conventions. The other one, yes, NetCDF library. Well, right now, I don't think they can do any of this, but they already do have some, for example, NetCDF dimensions. They are already something else in HDFI files. They just choose to present them as NetCDF dimension. So since they are an API above HDFI, they have ability to see what's the most appropriate representations for these things for the NetCDF data model, and then incorporate that in that way.
Once they've done that, then
Yes. Because yes, if NetCDF doesn't move in this direction, especially for this community, this may not be really relevant much.
Okay, we have one more question in the back here from Jim.
So I was just wondering to what degree you guys have considered possible ways to allow that reference to be resolvable in multiple fashions. In other words, like if I have the file, the external file next to the file on my file system that could find that, or go out to the web, because I can see the situation arising where it's like, well, I'm saying I'm pointing here at this S3 bucket or whatever, but then if I happen to be offline, or HTTP or whatever, I happen to be offline, but I have the other file here, that it would have some sort of fallback mechanism to go find the file, in one of the other, access modes or whatever. So I'm just wondering about that.
Since you're in the what could happen mode, yeah, that would be obviously, reasonable heuristic to go around. I mean, even now with these external soft links, and I think to the effect to what Quo mentioned, this virtual data set, because they're also file-based right now. There is some logic that goes and says, let me figure out if the file is in exactly there. Well, if it's not there, then let me think if it's in the current directory, but if it's not current, let me try some other things to try to find it. But and so that would be essentially the same thing. What I would like to see is that the library really switches between HTTP and something else all by its own. But even because right now in the S3 VFD implementation, which is still the kind of beta, I think, you actually have to change the code to make your code aware that it's going to work with the S3. What I would like to see in the library is that it's only an HTTP request, or even S3, / this. And the library itself knows that, I'm not working with S3. And so I'm going to do it by myself. That would be really the most powerful change. Because if I have to change my C code or whatever else to have versions that work with S3 and then work with something else, then it's more burden on the programmer.
Okay, any more questions for Alec? Not, we'll move on to the next.
Lunch is kicking in.
Lunch is kicking in. Well, they're all eating their lunch already. Okay, the next talk will be Robert Wolf on external geolocation for swath data, I believe.
Yeah, probably should have said a PDF.
No, this is fine.
Translates.
There you are.
Wolf with an E. Yes.
Okay, so I should just hit this, right?
Nope.
Okay, so I got to go up here. What did you like? I hit here, right?
Yeah, maybe something.
Yeah, there we go.
Good.
Take it away, Robert.
Okay, thank you. So just in case people read the agenda, it's the wolf with an E, but that's okay. So I'm going to talk about external geolocation. This probably should have gone first in terms of the slides, because it kind of actually motivates this whole discussion. So I guess the first question is like, why external geolocation? The swath products are, I think we all know this, are in the original instrument geometry. They're not gridded. And geolocation information is not only needed for remapping to a grid, but actually to understand the product in its context. The geolocation data can be large. It can be larger than some of the level 2 products, actually very much larger than some of the level 2 products like the snow products. And storing this information in each level 1 or level 2 products increases the archive volume. And for people who work with multiple products, it actually requires them to download duplicate data. So I'm going to, in this talk, I'm going to use MODIS as an example, but there are other satellites and aircraft data that have these similar issues. One in particular is VIIRS, has a very similar issue as we produce, other data does as well. I want to make a distinction. Some people, when they say level 1 data, they think of Landsat level 1 data, which is already gridded. And I'm not talking about that type of level 1 data. I'm talking about the ungridded swath formatted data. So this is the MODIS instrument. For people who are not familiar with MODIS, we have 36 spectral bands, data resolution from 250 to 1 kilometer, daily global coverage, a fairly wide swath width, not quite wide enough to cover everything at the equator, but almost. We have the first one was launched 20 years ago as of December this year. And the other one was launched about 18 years ago, 17, I guess. It was launched kind of in June. So it's a big instrument. It's a lot of data coming down, and there are a lot of products associated with that. Level 2 products in particular, and then higher level products, gridded level 3 products. So, well, what is geolocation? Well, first of all, it's the latitude and longitude of the observed sample or observation, either the sample or pixel, whatever you want to call it. And for terrestrial applications, looking at the Earth's surface over terrain, you have to do a terrain correction. And things like decimating the geolocation, which can be done over oceans, and for some many atmospheric applications, you can do the decimation and store every 10th, 5, 10, 20th pixel. And actually, the geolocation storage issue isn't as much of a problem. But for terrestrial applications in particular, land applications in particular, it's a difficulty in terms of storage and duplication and so on. But when I think of geolocation, it's just not the latitude and longitude. It's other observational geometry information. It's like the height above the geoid, the sensor range, the sensor view, and solar angles, as well as quality fields. You know, whether we were even able to do a geolocation at a particular point. And so, and it's really useful for, you know, not just gridding, but it's for understanding the context of the observation. So where was the sun when that particular point on the ground was observed? How were we looking at the point? So if you're doing things like BRDF retrievals or other types of things, you really need to know the geometry of the viewing that occurred when you saw that pixel. And this geolocation is for land applications in particular. It's computed and used for every observation, and particularly if you have rapidly varying terrain, you want to do it at whatever the resolution is of your particular satellite observation. And so for MODIS, we were doing this back in '99 when we originally designed it. We actually only compute the geolocation for every 1 kilometer pixel, even though there are 500 meter and 250 meter resolution pixels in the data. At the time, it was not feasible to compute it at 250 meters. We've done some kind of weird things with 500 meters in the interim, where we compute an offset at 500 meters and then store it in like a really compact way. And we're thinking about maybe doing something similar to that for 250 meters, but there's some additional computations users have to do on their end to unpack that. And I'm not going to really talk too much about that. I'm not going to talk about that anymore today. So this slide is kind of busy, but it actually gives you an idea of the different products, different number of granules or files per day for each of the products that were in the level 1, level 2 land and atmosphere products. I didn't really consider oceans because they have their own approach to doing this. And the size of the granules, but I also, and then the total data volume. And you can see some of these are quite large, 20, 30 gigabytes a day. Surface reflectance is about 50 gigabytes a day. Just varying sizes of all these products.
And then I did some computations on these various products and looked at, what the current volume is. We basically have about 159 gigabytes per day. If you multiply that by 20 years of Terra and 18 years of Aqua, you get about 2 petabytes to 2.1, 2.2 petabytes. A lot of these products already have some sort of embedded geolocation. And when I talk about embedded geolocation, it's usually a subset of all the geolocation products. You can see the geolocation product by itself is about 8 gigabytes per day. But these reduced, they have like either they store latitude and longitude only, or they may store a reduced resolution version of the latitude and longitude and some of the parameters and so on. So I went through there and kind of looked at all of these guys, and instead of putting them all up on a chart, I just kind of summarized the size of this embedded geolocation subset. And all these the big number, the first numbers are always in gigabytes per day. So for the calibration, we have about 6 gigabytes per day of embedded geolocation, which is almost actually the same size as the geolocation, but it doesn't contain all of the geolocation information. And it doesn't contain the same information. It doesn't contain all of the information for all of the files. So if you're working with 1 kilometer, you don't actually have the 1 kilometer geolocation, but if you're working with 500 meters, it gives you, it's a kind of a weird kind of way of doing things that kind of looking back on it, I kind of wonder why we did it that particular way, but it's the way it is, and it's been that way for close to 20 years. But if you look at, for instance, level 1, it's about 9% overhead for storing the geolocation embedding the geolocation in the file. So that's it's not a big overhead. And I think you kind of look across the board at the different products, it turns out to be about 7% overhead for storing the embedded geolocation, which turned out to be a fairly good solution for the time. But it's still, you don't get the full resolution geolocation. And if you want the full resolution geolocation, you have to order it separately. And I also looked at, so I guess that's the next to last column shows you what the size of the file would be if we did not embed the geolocation. And then if we actually embedded just not the full geolocation, but just some of the geolocation in the files, each file, each level 2 file, the geolocation at 1 kilometer plus some view angles at 5 kilometers, what the size of the files would be. And actually it would be about 30% larger if we embedded what I would consider, a good amount of geolocation in those files. And actually you can see, for instance, for some of the level 2 land, that actually the range, I think it was the snow product, which is the worst case, which really compresses well. If you just start adding almost any geolocation at all to that product, it expands very dramatically. It gets up to, and there's no decimal point missing there. That's 5,000 times, or 5,000%, so it's like 59 times as big as the raw, it's just the data by itself. So that's kind of the motivation. So this is actually my next to last slide. So it's my last slide. So what do we need? I think we need better support. First of all, when people distribute the data for level 1 and level 2 data, it should be easy for the users to automatically download the external geolocation files. It should be like, one of those market, Amazon does this. You bought this product, why don't you add in this other product? So we really need to have that happen automatically when people order these data, and just so the users are aware that they're there. We just heard from Alex about, we need to have better support for this in various formats, and certainly HDF5 is a good example, but NetCDF in particular, since that's where most of the community is actually adopting the NetCDF library and using that as the primary interface to a lot of our data sets. External variables are allowed in NetCDF, but there's no convention for specifying where to go to get that external variable. So you can say my latitude and longitude are external, but
you really want to say, where that's located. And you actually want to be able to do it not just for latitude and longitude, but for any of the geolocation variables. And there's some things that we could do, and I didn't really talk about it here. The geolocation data is kind of meant to be the center point of each observation. Well, that works for the 1 kilometer data, but for the 250 meter and 500 meter data, which of the subsamples within that sample does the geolocation correspond to? In some cases, it may actually be halfway in between 250 to 500 meter samples, and there's some other approaches to nesting where it's something a little bit different than that. So the nesting thing has to be kind of thought about and handled, and then even the ability to decimate, just store decimated geolocation, but then have an automatic way, like the ocean team does with their toolkit for populating it for each individual observation. And that's the very last point. The user tools and libraries should allow for external geolocation. There should be enough information in the file format to relate the geolocation information to the actual observations, and there may be band offsets and other types of things you may want to account for. I think remembering back to what we did with HPF EOS, there was quite a bit of thought given to, how a geolocation value would be associated with an observation, and we did quite a bit of work in terms of, the geolocation is, oh yeah, it's the first or second or third pixel in the array in this direction, and there's a number of things that we did in the HPF EOS format that we should probably look at and see if we can adopt those or actually maybe make some improvements to those. So that's all I had on that. So questions?
We got plenty of time for questions for Robert.
Yeah.
Trying to get the mic going here. It seems it died or something.
I can just restate the question if you want.
Yeah.
My question is,
Test,
how
test.
is the connection known at this point today?
It's just blinking red.
Between the external geolocation file and the data file?
The question is, how is it currently known? How do we currently know the relationship between the MODIS standard file or level 2 file and the geolocation file? It's assumed that the user knows. It's documented in a user's guide.
Test.
That describes the geolocation. So it isn't easy for the user to actually know that.
Mic's working now.
It's not just that. You have to actually be parsing the file names, right, to match up a Modo 3 with, a Modo 2 1cam or something like that.
Yes. There's no. I mean,
And
we do
Lord help us if the
provide
production time is different. Lord help us if the production time is different.
So yeah, I mean there is a input pointer. So if the processing to produce that level 2 file used a geolocation file in the processing, it usually has an input pointer which would be to that geolocation file. But you would have to parse the HPF EOS metadata to find that input pointer and then figure out that was the geolocation file. So I think it's probably, if I were writing code, I'd probably just parse the file name and find something locally and that's probably what I do when I write my code.
But I have another comment about another pain point, which is kind of maybe implied by some of that stuff. So I did a machine learning project with MODIS level 1 and level 2 data back in the early aughts or something like that. And the biggest problem for us was not just matching them up. It was managing immense amounts of data. And now I had to manage both, a set of level 1Bs, a set of level 2s, and the geolocations to go with that. And so it makes the data management problem for the user difficult as well. And as data get bigger and bigger and bigger, that data management problem is also going to get bigger.
Yeah, yeah.
You need something that's not fragile, it's not brittle for that relationship with the geolocation file.
I agree, and I think what we were hearing earlier is there's approaches to do that that can make that more robust and less fragile. And but yeah, I mean, that's why we try and jam everything into one file, is because as soon as you start creating linkages between files, then you have a kind of a data management nightmare on the end user end
Right.
to
And
do
so,
that.
so if I could riff a little bit off on one of your suggestions where you
Right.
talked about the ability to automatically download the level 3, I mean the external geolocation, is maybe there should also be an option at the user's discretion to embed the geolocation in those download
Yes.
files.
That's a very good point. I agree with you. Yes.
There's a question there then.
Okay, Jim.
Great minds think alike. So riffing on what Chris was saying, I was thinking of that in terms of just geolocation as a service. In other words, if the minimum metadata I would have about level 1 is I would have the granule ID. Okay.
Yeah.
If I don't have that, I'm screwed. So therefore, if I have the X and Y coordinates within the swath granule, okay, then I should be able to give it a coordinate range to this service and say, give me the geolocation, and get back that array that would have been embedded. So I wholeheartedly support the idea of, or just order it with an extra 2 bands that has the geolocation information.
Yeah.
Or if I have some lying around that I was stupid enough to not get it in the first place, I can go back and get this later, maybe even get better than would have shipped with it because of reanalyses that have been done on like the satellite position.
That's a good point. Yeah. And I agree with that. I think, I was thinking kind of in the download and local type of processing when I was putting together this support slide, but I think there's all sorts of things you could do in the cloud to make sure, whenever we get to level 1 and level 2 stuff in the cloud, and I don't think we're there yet, but as we do that, how you handle that geolocation and make the linkages to the geolocation is going to be really important, and we should, try and get it right, as we do that. So I thought there was another question.
Is there another question from the audience? Oh, back there, Joe.
So how many users contact your DAG that they can resolve geolocation properly? Do you have any stats?
I could find them. I should. That's a good point. I'll look and see what we have. To be honest, if you look at the usage pattern for the products, the level 3 products are used a lot more than level 2 products. So we've already gridded them. We've already composited them. We've picked the best observation. So the number of users who are using level 1 and level 2 products is actually fairly small, but they tend to be power users. They tend to be users who really want to dig down into the guts of the data and actually do science and don't tend to be just random people off the street. So I think, one of the things you could do, and I think there's probably some of the audience is going to respond to this. Yeah. I think what you can do
we'll take like 2 more questions and we'll move on.
By lowering the barrier, by doing things like this, will actually increase the number of people who are actually using these level 1 and level 2 products.
Yeah, it's the chicken and egg problem. And in particular, if this kind of data could reliably be delivered with geolocation information, then it wouldn't be, you wouldn't have to deal with people like me who are like groveling in there and assembling it ourselves.
Yeah.
But the people who are using ArcGIS or using MV, it would be worth their while, those companies' while to write the adapters that would allow it to eat that, and then they could do analyses with that in commercial environments.
Yeah, and it's just as simple as when you're selecting a file name, and you get a file that has an external geolocation file, it automatically will either allow you to put that name in there or will automatically go and use that link to find the external geolocation. And yeah.
One final question from Jim.
Okay, Jim.
So it's more of a comment, I guess, just, you know, I liked what you said about order of the talks could have been interestingly different, but my brain's just kind of on fire with the idea of like, you could, instead of some of the things we're dealing with here, you could make one stair, you could make a variable in your file that would be the stair index for each one of these things. So now you've maybe doubled your data volume, but you haven't tripled. Tripled it, for example, and then you've gone to the spot where it becomes very straightforward to say where is each one of the pixels in this grid, kind of a thing.
Yeah,
So that
I agree with you, and I think I'm intrigued by Quo's comment about the compressibility of the stair. I think for our purposes, we always our goal was to get the geolocation to within one meter, and any finer resolution than that is probably not. I mean, it's actually probably less than 10 meters, but I think, you know, you have to look at that differently for each type of data you're looking at. If you have higher resolution data, then you'll have to go, you know, store it at finer resolution. So,
okay, thank you, Robert.
well,
Yep. So I will be the final speaker here. Okay. All right, so I want to get back to the theme of where I'm going to present a few use cases of different parties. One of them I've been closely intimately involved with. The other ones is just something I found out about a few months ago, but they're examples, the new examples of encoding satellite geolocation information that reduce the footprint size of the geolocation grid information in two different ways. So, okay, so these are novel geolocation encodings for both examples for level 1 and level 2 satellite data. So these unstructured, ungridded swath products that the power user community uses. But increasingly there's some clever users that, after a few years of using gridded data products, they want to do something with the original data, right? And so they go back to the level 2 data. So implementation 1 is encoding geolocation for the geostationary GOES 16, formerly known as GOES-R, with the GOES ABI sensor that measures atmospheric and oceanographic observations. So I was specifically involved. I'm working with this group, the Group for High Resolution SST, for a long time, and our NOAA partners have a GOES 16 SST data set. There's a data set landing page, and we leveraged the new CF technique, leveraging on CF projection information to reduce the footprint. That's the first implementation. The second one is something I just found out about a month ago. UMetSat community has developed a new way of encoding geolocation for the VIIRS on NPP. So VIIRS is the MODIS-like kind of follow-on instrument. Doesn't have as many channels as MODIS, but it's it's designed for the all Earth systems observations of the atmosphere, of the land and the ocean. And so they've developed a new pixel level interpolation technique that allows them to decimate the geolocation information and then retrieve this subsample geolocation information using an interpolation technique. So I'll go through that. That's the one that's new to me, that I know the least about. So I'll start with the first implementation. So, okay, the first thing is the Group for High Resolution SST GRIST has a specific data model for encoding level 2 geolocation, latitude and longitude, and we do package that on a pixel by pixel basis in every level 2 granule. So every pixel is assigned a unique lat long, but as floats right within the structure of this particular NetCDF data model, it's the heaviest footprint of all the variables, which are scaled ints or bytes. And there's a link there just to see our GDS, what we call the GDS reference documentation that describes essentially the data and the metadata model all these international GRIS products. So this is a geostationary sensor that has an observation disk. Essentially, it's an unprojected grid. You can almost think of it as a grid, but it's not a grid, right? It's basically an unprojected space. And in this case, we were able to use the grid mapping CF metadata attribute and reference a projection called geostationary, one that was specifically developed for geostationary satellites. And if you go to the documentation, they actually have some attributes in there, some projection attributes that are germane to just the GOES series of satellites versus the spinning MEDOP series. But we were able to implement this. So how does this look and perform? So just go back a little bit about what a standard L2P, we call L2P, it's the P stands for pre-processed in the GRIS lingo, what it looks like. This is the net CDF CDL. This is typically where we see the dimensions of an NJ and NI, and the latitude and longitudes are now two-dimensional grids, right, to describe every single point in a swath. And then, of course, the sea surface temperature is also two-dimensioned. And the coordinates are listed there, long lat. So, the tools like Panoply or other visualization tools can easily use this, take it up, plot it up, and visualize it right on the fly. So that's the way the previous version of this GOES 16 data set from NOAA looked like, right? So it had a two-dimensional latitude, longitude, their floats. And this is what we came up in this new version for the GOES 16. So we still have the same dimensions, but now what we don't call them latitude longitude anymore, because they're actually just projection points. They're just NJ and I, which are one-dimensional location variables, right? And as we look in the sea surface temperature array, there's that grid underscored mapping attribute that points to the geostationary projection scheme, right? And so that's the key there. That's the key in this metadata model of how to describe this projection information correctly, so that a tool like Panoply or other types of readers can take that information and then plot it up. So I forgot to mention, okay, this is the NJ and NI are in the original satellite projection frame, so they're in radians, right? And their standard name is projection underscore Y coordinate and projection underscore X underscore coordinate. So in addition to this geostationary, essentially it's a projection tag. You have to have an additional, essentially a dimensionless variable inside here that then describes the entire projection information for this particular one, which is called geostationary. And we see all the semi-major and the flattening and all the false easting and all the information that the software reader, like such as built-in Panoply, uses. And as I pointed out, there are some specific GOES attributes in this projection, and that sweep underscore angle underscore axis equals X means something very specific to GOES, the GOES suite of geostationary sensors. So they're essentially their viewing structure, I guess, or their viewing geometry. Okay, but once all that's defined, you can just take that granule, you just whip it into Panoply, and it plots right away, just like any other level 2 granule that is part of the GRIS product suite. So no difference there. Panoply, the developer Panoply, understands these CF projections, and with the proper tag, the grid underscore mapping tag, it knows exactly what to do. So that was one successful use case, and just kind of shows. This slide shows some metrics here of the actual granule data reduction that we were able to obtain with this. So on the left-hand side is the previous version of the GOES 16, and on the right is the one that leverages off the new CF geostationary projection structure. And so we were able to go essentially from about 270 megabytes down to like the low 40 megabytes, so an 80% reduction in the size of the granules. And this is compressed sizes that I'm showing right here. So this is a pretty substantial reduction, where we able to go from something on the order of a few gigs, like 4 or 5 gigs a day, down to kind of the 100 megabytes, like an order of magnitude less. So I think it was a success story, but I'll have a few other comments at the end of my slide set here. I'll move on to the next one. So this is something I found out a few months ago, as I mentioned. This is the EUMETSAT, which is the European Weather Agency. They have developed this level 2 VIIRS compact data model, and they actually have a complete document on it that you can get on the web. And so, here's some language directly from the introduction. A need was identified to develop a compact VIIRS SDR product format to achieve a cost-effective distribution of VIIRS data via UMETSAT satellite-based data distribution. So for their internal customers, I imagine is they came up with a requirement that they need to reduce the size of these VIIRS level 1 granules, which are quite data dense, right? So the other things I pointed out, highlight here. Okay, so the original product format. And so this document describes how to construct the original product format from the compact data format. So let's go look and see what that compact data format is. So essentially the compact data format is the geolocation that's been decimated, and you only store 4 corner points. They call them tie points in their language, in conjunction with two other parameters that deal with the satellite look angle, and then you apply interpolation functions that are defined for this reconstruction of the geolocation points for all pixels within that tie point zone. So here are a few screen grabs from the document itself. So this is the original layout of variables, geolocation variables, and other variables within this level 1 product. There's 3,200 pixels in the scan length, and there's a 767 along track pixels. So just keep that in mind. And now this diagram shows the actual subsampling and decimation. So what we're looking at here is a 16 by 16 grid of the M-band pixels. These are the lower resolution, about what is VIIRS? 700 meters, right? So we were decimating this 16 by 16 grid, and we're only keeping these 4 corner points, right? These 4, the A, the B, the C, and the D. So the latitude and longitude for those corner points are stored, as well as 2 angular parameters for that view. So you're reducing the size from something that's 3,200 pixels wide, and now we're down to only something that's 200 pixel wide by 95 pixels, right, along a long track. So you're both decimating in both in the along track and the cross track. So the next slide, final slide, is they present some formulas about how to, what is the mechanism, the interpolation mechanism to reconstruct an original latitude, longitude, and these are the 3 formulas you have to apply here. Of course, the lat and longs, the A's and B's, those are the tie points from that 16 by 16 grid, and the alpha scan is a constant, has to do. If I read the documentation correctly, has to do with the changing pixel width as you move across the scan line. It's some kind of a constant that's calculated. And so once you have all that information, you basically, if you want to derive a point, derive an original latitude back from the decimated grid, this is the formula that you would have to apply for the corner points A and B and the corner points D and C. And then basically you apply this third step here, where you're taking the first 2 latitude, longitude sets, right, and then applying this third step. So it's complicated, right? So it looks a little bit simple, but you can imagine that this is not trivial to set up like in a software reader or in a software visualization tool. You have to really pay attention to what the formula is and to apply it correctly. Okay, so that's my last slide. I just have a few summary points here, and in the case of the geostationary, the GO16 with the NOAA folks, it really provided an elegant roadmap, to allow us to basically take that projected space and basically, essentially treat the geostationary observations in the original quarter system almost like a grid, right? And allow on the software side that to be plotted or to be usable. we incurred like an 80% data reduction, which was pretty significant. But of course, those original coordinate systems that I showed in the CDL, right, that's all in radians in the projected satellite space. So, you know, a lot of people, if they were opening that up in NC dump or something like that, they might be very confused about it initially, what they're actually looking at, right? The second example, I show that UMetSat had developed a data model to decimate the original observations and just keep a subset and then be able to interpolate back the geolocation information. And there's also probably a substantial size reduction there, probably also kind of close or order of magnitude, similar to what we saw above. But you know, you need to apply some pretty complex interpolation to be able to retrieve the original geolocation. And you know, the question I have for that community is, you know, what kind of software developers have started tackling this? You know, I plan on reaching out to that group UMets. I don't know really who they are, but I know some people that work in the UMets community that I could potentially leverage that might help me, you know, track down, you know, where they are on as far as, you know, working with software developers to be able to implement these interpolation algorithms. So I think that's it. You know, what else is on the horizon? I'm open to some questions now too. I think we have plenty of time for discussion.
Is the red good?
Yeah, the red was good for some reason. At least the mic was hot when the light was red. So I don't know what the.
So we tried this, you know, reconstruction from decimated tie points, you can call them that, with the MODIS data. And the problem that we ran into there was that it's really 10 cameras, right? And there were tiny little, you know, alignment differences between those cameras, so that you couldn't really assume that, you know, the pattern, the spread pattern was even.
Mm-hmm.
And it was off enough that it wasn't really usable for our purposes, so we had to go back to the main Modo 3. Now, it seems like you could fix that if you also had the pattern of how those individual sensors inside that FOV are aligned.
What MODIS product was that you're talking about?
He's talking about the MODIS, I believe, yeah. So, yeah, I want to make a couple of points on your chart. First of all, I think, you know, the by using the well, first of all, the GOES data is already gridded. So what the first thing you did, which I'm not sure why, you know, they provided latitude and longitude product anyway, because you just provide, just like you did. That makes sense to me.
It's not a perfect grid though.
It's
yeah.
Okay, yeah.
There's like a little wiggle.
Yeah.
Yeah, and
so the convention, yeah, it's not a perfect grid, but it is. You're not working with the level 1 beta data, which is in the original swath format from the instrument. That's all been handled. So it's anyway. But to go to Chris's point on the MODIS, yes, and for VIIRS as well, we could with the for the non-terrain corrected data, interpolation can be done. So if you're not using the data that's been terrain corrected, yes, that type of interpolation will get you pretty good accuracy. And I'm not sure what their claim in terms of accuracy is. It may just be, you know, sufficient for their particular needs. But if you're working with terrain corrected data, you would have to provide an additional offsets for the smaller terrain information that you could not possibly know from those 4 corner points. So I think, but I, you know, the Ocean Color Group, I believe, which you mentioned earlier, has already done something similar to this for MODIS, and when we provide what we call 5 kilometer geolocation in our products, we expect the users to do something similar to this to interpolate to 1 kilometer, which is what they really need. And so it's really complicated. This type of thing is complicated by the terrain correction. But I will say that for MODIS, and I didn't really talk about this, when we decided to provide the 500 meter geolocation in addition to the 1 kilometer geolocation, we assumed that the users were going to interpolate correctly between the 1 kilometer observations in something
in a manner similar to this.
Mhm.
And then what we did is we provided the small deltas between those interpolated points and the true points. And that accounted for the jitter of the terrain correction,
Mhm.
which
But
and those small corrections actually go almost to zero when you compress them over the ocean because there's no terrain. And over most land areas, the terrain is, if it's smooth, then those corrections are very small. So
are those corrections like static? They're just like they never change, or?
no, they're provided in the product. They're just a separate array. So, and we've described in our geolocation user's guide how to reconstruct it. But of course, nobody reads those user's guides. Well, you read this one, so yeah. I mean, actually, I shouldn't say that. There's at least one person who reads user's guides.
And on that very honest, any more questions?
I have one more question or a comment. This is Peter Leonard speaking. It was mentioned about including an external link within a file, and it was, the example was for a stair file. Just the issue is that your data file may have been produced 10 years before the stair file, so you'd have to put like an empty link inside the original data file, and once a companion file is available, that would have to be populated as the file is brought out of the archive. I'm just saying, the companion file isn't always produced at the same time as the data file. They can be produced years apart.
Yeah, I think that was getting back to like Jim Prue's observation. You could have this geolocation service that would, based on like better satellite ephemeris and whatever, better orbit description, could provide like better geolocation on the fly after the fact. Well, no more questions. I guess we'll close this session then. Thanks a lot for your participation. Hopefully you enjoy the presentations, and let's give the presenters a final round of applause.